So in the last lecture, we looked at this data and saw that while the sample size was changing variably, the percent change was constant. So if we graph the time values versus sample sizes, we get something like this. Now, as we talked about before, some of you may already know that radioactive decay can be modeled exponentially, but we want to think about this without any previous assumptions or understanding, right? If you were just presented with this data without any kind of context, how would you analyze or model it? Right now, looking at this graph with that in mind, it isn't particularly helpful. On the one hand, yeah, it does appear to be exponential. However, a parabola or a quadratic curve within certain ranges can look very similar to an exponential curve. And unfortunately, the human eye and the human brain are not very good at distinguishing between the wide variety of graphs and relationships that come up in mathematical modeling. So let's take a step back and think about what we saw in our previous analysis, right? We saw that the percent change was constant. That is delta A sub n divided by A sub n equals some constant k. Or, if we manipulate this a little bit, delta A sub n equals k times A sub n. So what this says is the change in the sample size is proportional to the sample size. So now I've reduced our data table down to just those two columns, the population values and the change values, right? Now on the last slide, we saw that the relationship between these two things should be linear. And if we graph them, we get this result. Now, while we may not be very good at distinguishing between things like exponential and quadratic curves, we are really good at identifying straight lines. And that's clearly what we're seeing here. Now, before we go any further, I want to be clear about what I did here, both mathematically and conceptually, right? First, I looked at the raw data, the time values and the corresponding sample sizes. I graphed them and realized that the result wasn't very informative, right? So I went one step further and looked at the changes in the sample size. And when I graphed those two results with respect to each other, I got a graph that I was able to identify, something that was clearly a linear relationship. Right, so in terms of the actual graph, what I've done is I've put the sample sizes, those would be the A sub n's, on the x-axis, and the change values, those are the delta A sub n's, on the y-axis. Right, so what have we seen here, right? We got a good model for the change in data. We can see that that's a linear model, right? And I want to take this a little further, right? I want to take this and see how we can sort of work this back to a model for the actual data itself. Okay, I want to kind of put this on hold for just a minute because in the next lecture, I want to look at a different scenario and look at a slightly more complex model. Right, then once we've got a little more background in coming up with the model itself, we'll circle back to this and look at how we can kind of keep moving forward toward finding an actual model for the data rather than the change.